mass, this reduces the gravity activity somewhat. So the flexion is 10 times less mass.
リアルプレイヤーの収録外で。
And then this assumption has been made usually that we have a lot of dark matter, but the primary reason for this has mostly been due to the fact that we haven't really had a very compelling non-Newtonian gravity theory, which most of them were just ad hoc models explaining very
昔の2006年ぐらいです。
It was very difficult to distinguish these out from observations of other phenomena. Over the past couple of years, though, people have been coming up with models which could be derived from general relativity, and therefore you can extend them to things like gravitational light, CMB observations, and light. And that's actually sort of been a small explosion in the number of papers coming out doing that. And one of the primary problems is if you take normal galaxy clusters, these are two fairly massive clusters, Babel 1689, 1835. These are sort of used as archetypical belt clusters. And what you see is these are some weak lensing observations we made. The contours are on kappa, and you can easily detect them. However, all the galaxies and all the gas is all located in this area along with any dark matter. So it's relatively easy to prove that there's way too much gravity here. But you can't really distinguish between whether this gravity is dark matter or whether it's extra gravity on these large scales without going into very fine details. So what we wanted to do was take one of these systems, and if you could take it into a physics lab here on Earth, the obvious thing to do would be to separate out the various mass components and weigh them and see what actually has the mass. And so what nature does this for this is in collisions of galaxy clusters. So if you take two clusters of galaxies, they have a lot of galaxies, they have a lot of gas, and they have a lot of dark matter, and you get weak lensing observations that's saying that there's a lot of stuff in here with too much gravity. And then if you collide them together, the galaxies are basically collisionless particles, whereas the gas is fully collisional as the two gas clouds pass through each other. And so you have ram pressure, allows the gas clouds to trade momentum. And so after the collision and they're moving back apart again, you have the galaxies moving away, and the gas is going to be forming a large pancake in the center. So now you have a physical separation between these two, and now you can actually look, and if there's any dark matter should also be largely collisionless, so it should be up around the galaxies. And so then we can take gravitational lensing, and if the dark matter solution is correct, then we should see the gravitational lensing is up around the galaxies, because this is where the dark matter is, and the dark matter is something like 85 to 90% of the total mass of the cluster. So only 10% of the gravitational potential would actually be back here. If, on the other hand, you want to explain these using some form of altered gravity and not have any dark matter, then 90% of your baryons are now here in this cloud, and this is also where you would sort of expect all the gravitational potential and lensing to be in. Now, things aren't quite as simple, I'll get into that a bit later, but it's still a fairly hard concept to get around of how do you not have the gas cloud be the center of the gravitational potential. So, just to do a quick definition to make sure everyone understands the terms that I'll be using, what we measure is we take galaxies, we measure their second moments of the surface brightness, you correct for the point spread function, and every galaxy then gives us a measurement of the reduced shear G, where gamma is the gravitational shear. This is the anisotropic change of the shape of the galaxy from the gravitational lensing, and it's related to some various second derivatives of the surface potential. You also have the convergence kappa, which is the isotropic change in the shape of the galaxy, overall increase or decrease in its size. It's also second derivatives of the surface potential, and in Newtonian gravity, this is also simply equal to your surface density divided by a geometric scaling constant. In non-Newtonian gravity, that's no longer true. Now, we measure this. We ultimately want to get this as the most direct measure of the mass. One way which you can do that is you can take the gravitational shear, because these are both second derivatives. You just simply take derivatives of your gravitational shear, combine them. You get derivatives of kappa, which you can then integrate, and you basically have kappa with an integration constant, which is the mean kappa at the edge of the image. Of course, we're not actually measuring shear, we're measuring G. You can still do this. The equations are a bit nastier, and what you're actually winding up is the gradient of the logarithm of 1 minus kappa, which means you still integrate that. You still have an integration constant, which is sort of the mean value at the edge of your image, but it's no longer a simple additive. It also shows up as a multiplicative value, which complicates matters a little bit, and so you want to basically try to minimize this by getting very large images so that your kappa at the edge of your image should be very close to zero. Now, the system which we're going to use to do this is 180657. This was discovered back in the, I believe, early 90s as part of the first Einstein survey. And what you see, here's one group of galaxies over here, here's one group of galaxies over here. If you'll notice, this is an HST image with a very nice star. This is a Magellan image. This is one of the benefits of doing a press release, is you have people who are very good at graphics doing this. I have no idea how they color matched these two groups here. But all these sort of yellowish-orange galaxies here, these are all the cluster galaxies. And what you'll also notice, and we'll come back to, is that in the main cluster, you actually have one core here, and you actually have a second core here. These are both CD galaxies. This guy has a couple overlapping things, make it kind of hard to see. So this isn't a nice, simple, relaxed system as our main cluster. Now, if you look at these in the X-rays, it becomes a lot more easy to see what's going on. Here's your main cluster. Here's the smaller cluster, and you can see out in front of the smaller cluster is a bow shock. This is a supersonic bow shock. You get a change in temperature, in density, and the two combined give you actually a change in pressure, which is how we know that it's supersonic. You can actually measure these. We get about a Mach 3, and you take the temperature and density of gas in front of it. That has this thing moving at about 4,700 kilometers per second relative to this gas cloud. If you overlay this on top of the optical image, you get exactly the picture that we drew earlier. You have the galaxies which were only slowed by tidal forces during the collision are moving faster, and this is now about 100 million years after the collision, and they have now moved out in front of the gas. Exactly what we expect. Nothing surprising going on here. So now what we want to do is we want to go and we want to try to measure where the gravitational potential is using gravitational lensing. And to do that, we have to assemble a whole bunch of deep optical images. We put out a paper in 2004, which was the first attempt at this. And for that, we used an image which we found in the VLT archive that was taken during commissioning. It was a relatively short exposure. You got about 11 galaxies per square arc minute over an 8 arc minute field, which was enough to sort of detect the clusters at about the 2 to 3 sigma level and get some rough idea of what was going on. In the 2 years since then, we've assembled a much better set. We have a wide image from the wide field imager, which is 34 arc minutes. This is about 8 megaparsecs at the redshift of the galaxy. And we get about 15 galaxies per square arc minute. The primary source of noise is the intrinsic ellipticity of the galaxies. And so the way in which you beat this down is you get more galaxies. And then we also went to the Magellan telescope, a 6.5 meter, also down in Chile, using IMAX. This gave us an image that was about an 8 arc minute radius, which we could use, inside of which we had about 35 galaxies per square arc minute. And then we also have 2 pointings of the Hubble Space Telescope using ACS, which gets us in around the bullet portion. We actually have 3 colors. We get about 90 galaxies per square arc minute. Around the main cluster, we currently only have 1 passband, and that limits us actually to about 60 galaxies per square arc minute. But the idea is that we're going, as we go in, we increase the number density of galaxies, which means that we're decreasing the noise. So we have, sorry? The clusters, so these 2 things basically have, the main cluster is sort of right there, the bullet cluster is sort of right there. So these 2 pointings sort of bracket it. Right, so then what we did was we took all these images, we create galaxy catalogs, measure the shear estimates in each image separately, and then sort of co-add the catalogs. You have to do a few small things like adjusting for the fact that your mean redshift is going to be jumping across the image, and so you have to account for that when you're measuring the shears. But I won't go into any details. But what we do is we take the final catalogs and we invert them and get measurements of kappa. And here are the contours, which you can see of kappa. And what you can see is we're finding kappa contours that are vaguely around where the galaxies are and fairly well not where the gas is. So from our earlier cartoon picture, this would tell us that we have lots of dark matter and not alternate gravity with only the baryons. Now, unfortunately, alternate gravity isn't quite this simple. Once you have multiple mass peaks, you get all sorts of nonlinear effects which can occur. And I'll go in a bit later as to what those can be. However, one question which you might ask is, we know weak lensing is very noisy. Is it possible that these mass peaks are actually on these gas peaks, and it's just noise is moving them away? To do that, we have to go into weak lensing and look at what sort of noises you have to deal with. Well, you have the PSF smearing correction. There's been a lot of effort in this over the past couple of years. We're pretty sure we have this down to a few percent. In a galaxy cluster like this, we're looking at shears on the order of 10%. So while this is still a concern for things like cosmic shear and even for galaxy-galaxy lensing, for clusters of galaxies, this should be showing up at well under 1 sigma in terms of what effect you can get. So we don't think that this can be a very big effect. Also, we have the 3 separate images which we can directly compare the values for the various galaxies, and we don't see any systematic biases between them. You have the intrinsic electricity of the background galaxies. This is not a whole lot you can do about this. This is basically shot noise. It shows up in your measurements. You have that lensing is actually looking at all the mass along line of sight, so you might have something that's not actually associated with the cluster projected onto it, and that could change where what you're seeing in terms of your kappa values. You have the mass sheet degeneracy. You can only measure the mass relative to a value at the outside. Unknown redshift distribution of the background galaxies. We go about 4 magnitudes fainter than what the spectroscopic surveys do. And then if we want to try to actually break this mass sheet degeneracy, typically what we do is we fit it with a mass profile family, such as an NFW. If you assume a certain family that happens to be wrong, you can get the wrong value for this and get the wrong mass. And also you have the fact that when we do this, we're also assuming that systems are spherical when they're actually probably triaxial, and that can give you all sorts of errors. However, only these 2 actually matter if we're not interested in how much mass there is, but only where it is. Okay? And this one turns out to be very simple to actually model, because what we have is we have a catalog of background galaxies. Each one is an independent measurement of the shear. And so what we do is we create new bootstrap catalogs in which you take every you have the same number of galaxies. Each new galaxy is randomly chosen from the old set, and you can allow the same galaxy to show up more than once. You put this through your same reconstruction method. You look for how your peaks move, and you do this a couple 100,000 times. And what you wind up with are these white contours here, which show you where 68, 95, and 99.7% of these are. And what you can see is noise can't be responsible for this. All right, so what does this tell us? Well, we can actually fit the masses. We get something like 2140 and 1000. This guy has probably been tidally stripped, so this is probably an underestimate of what mass was beforehand. But these are fairly massive, but not unusually massive clusters. We do see that the offset is about 8 sigma in significance. I said we can actually only measure it out to 4 sigma. The 8 sigma comes from assuming the contours don't change as we go up to higher levels. The X-ray gas is detected as a minor perturbation. What you might be able to see is that if you look at sort of the contours over here, these ones are clearly being extended. A analysis of this tells us that the gas is actually producing about 12% of the gravitational lensing, although that has about 100% error in its measurement. What you can also see is that the system is not symmetric. If you actually take a line between those 2, the gas clouds are actually sitting north of the 2. This becomes very important. Okay, so what does this tell us about gravity?